Okay, so we're going to continue in our lesson where we left off in class, looking at properties of rational functions. Okay, so we have a couple of definitions that we're going to look at. So we're told to let R be a function, and then it says if as x, and then when you see that arrow, that's going to mean the word approaches. I'm going to say approaches. But you can also think of it as gets closer to. Okay, so if as x approaches infinity or as x approaches negative infinity. So I'm going to kind of like teach you guys a little bit of calculus here without actually doing calculus. So these definitions are kind of like the calculus definitions, but we're missing like one aspect of calculus that you need, which you will learn next year in pre-calculus, which is called a limit. So we're going to talk about asymptotes here without looking at limits. So again, it says if as x approaches infinity or as x approaches negative infinity, the function r of x approaches L, then the line y is equal to L is a horizontal asymptote of the graph. Okay, now when we look at horizontal asymptotes describe end behavior. Okay, so that tells us like what happens to our graph as we move away from the origin in both directions. So as x goes to infinity and as x goes to negative infinity. Now, your graph may intersect a horizontal asymptote, but it must do so locally. Okay, so when we say a graph can cross a horizontal asymptote, but it must do so locally, when we say it must do so locally, that means it has to be in the vicinity of or in the neighborhood of the origin. So it's not going to cross a horizontal asymptote as your x values go to infinity or as your x values go to negative infinity. So what I want to do is I want to come back and look at these two functions here that we left off looking at in class. So we have the function 1 over x and the function 1 over x squared. So if we look at that definition for a horizontal asymptote, it says that as the x values go to infinity, okay, so I'm going to draw this in red. So as the x values go to infinity, and as the x values go to negative infinity, if we look at the graph of our function, I'm going to highlight this in blue. If we look at the graph of our function, the y values of our graph get closer and closer to the y value of 0 on this side, and the y values of our graph get closer and closer to the y value of 0 on this side. Okay, so if as x goes to infinity or as x goes to negative infinity, the function values or the y values approach some finite number, which in this case, it approaches the finite number of 0. That tells us that our graph here has a horizontal asymptote at y is equal to 0. And we can do the same thing for the function 1 over x squared as well. Okay, so again, if as the x values go to infinity or as the x values go to negative infinity, if the y values of our graph approach some finite number, which the y values here are getting closer and closer to 0, the y values over here are also getting closer and closer to 0, again, that graph on the right is going to have a horizontal asymptote at y is equal to 0. So anytime we find an asymptote, we have to write the asymptote as the equation of a line. So a horizontal asymptote is going to be the equation of a horizontal line. It's the line y is equal to some number. Okay, let's look at our next definition. So our next definition says that if as x approaches c, the function r of x approaches infinity or r of x approaches negative infinity, then the line x is equal to c is a vertical asymptote of the graph. Okay, now your graph will never intersect a vertical asymptote. Okay, so again, if as x approaches c, r of x approaches infinity, or r of x approaches negative infinity, then the line x is equal to c is a vertical asymptote of the graph. Okay, so I'm going to go back to the graphs of these two functions. Okay, now I'm going to go ahead and draw this in green. Okay, so as the x values approach 0 from the left-hand side, so I'm going to draw that in green. As the x values get close to 0 from the left-hand side, I'm going to draw this in green as well. Okay, the y values go down to negative infinity. Okay, so again, if as x approaches 0, the y values go to negative infinity, or if we look approaching 0 from the other side, so as the x values approach 0 from the right-hand side, the y values here are going to positive infinity. Okay, so the y values are going to positive infinity. Then both of those tell us that our graph has a vertical asymptote at x is equal to 0. Okay, so as your graph approaches a vertical asymptote, your graph can do one of two things. Okay, your graph is either going to go to infinity as you approach the vertical asymptote, or the graph goes to negative infinity as you approach the vertical asymptote. Let's do the same thing for the function 1 over x squared. Okay, so as the x values get close to 0 from the left-hand side, so as the x values get closer and closer to 0, we look at the y values of our graph here. The y values of our graph are going to infinity, which tells us that our graph has a vertical asymptote at x is equal to 0. And we can do the same thing on the other side as well. Okay, so as the x values approach 0 from the right-hand side, so as the x values get closer and closer to 0 from the right-hand side, the y values here are also going to infinity. So both of these confirm that our graph has a vertical asymptote at x is equal to 0. So again, just like with horizontal asymptotes, vertical asymptotes are also the equation of a line. They just happen to be the equation of a vertical line. And we know that vertical lines are of the form x is equal to some number. Okay, now the next thing I want to mention is really important. It's going to be important whenever we start graphing rational functions in the next lesson. Okay, if you guys remember back to like polynomial functions, so I want to compare these two really quick. Okay, we have the function f of x equal to x squared and the function f of x equal to x cubed. And we said that the multiplicity of our 0, or the multiplicity of the x-intercept, dictates whether the graph touches or crosses the x-axis at the x-intercept. Okay, so we know for the function x squared, that has an x-intercept at 0, and because the multiplicity of that 0 is 2, it's even. That means the graph is going to touch the x-axis at that point. When we look at the function x cubed, the function x cubed is going to have a graph that looks like this. It also has an x-intercept at x is equal to 0, but because the multiplicity of that 0 is odd, it's 3, that means that the graph is going to cross the x-axis. Well, when we look at our denominator, so for this function it's x to the first power, for this function it's x squared, the multiplicity of our 0 on bottom also tells us something about the graph of a rational function. Okay, so if your rational function has an odd multiplicity in the denominator, that means that the graph is going to go in opposite directions as you approach the vertical asymptote. So when we look at the function 1 over x, when we approach that vertical asymptote at x is equal to 0 from the left-hand side, that graph is going down to negative infinity. But when we approach that vertical asymptote at x is equal to 0 from the right-hand side, the graph is going to positive infinity. So our graph is going in opposite directions at that vertical asymptote. But when we look at the function g of x, which is 1 over x squared, there the multiplicity of the 0 in our denominator is 2, it's even. So what that tells you is that your graph is going to be going in the same direction at the vertical asymptote. And for the function 1 over x squared, as we approach that vertical asymptote, both from the left and from the right, both sides are going to positive infinity. Okay, you can also, for a rational function with an even multiplicity in the denominator, have both sides going to negative infinity as you approach that vertical asymptote as well. So we'll talk later on about like how we can determine that. Okay, but again, odd multiplicity in our denominator means the graph goes in opposite directions. So one side is going to go to infinity, one side goes to negative infinity as you approach the vertical asymptote. And even multiplicity in the denominator means that as you approach the vertical asymptote from both sides are either going to go to infinity or negative infinity. Okay, again, really important idea for us as we continue moving forward in this chapter. Okay, let's move on to the third type of asymptote, which is more rare. Okay, you don't see as many functions with this type of an asymptote, but it's called an oblique asymptote. That is what I call it. Some other textbooks call it a slant asymptote. Okay, so an oblique asymptote or a slant asymptote of the graph is one that is neither horizontal nor vertical. Okay, its equation is of the form y is equal to mx plus b. Okay, so the equation of an oblique asymptote or a slant asymptote is going to be the equation of a line y is equal to mx plus b. And just as we said with horizontal asymptotes, oblique asymptotes also describe end behavior, and a graph may intersect an oblique asymptote, but it must do so locally. Okay, so it has to do so in the neighborhood of the origin. Okay, so let's get into some other definitions that I want to look at, and then we'll get into some examples tying everything that we've looked at so far in this lesson together. Okay, so we say that a rational function is proper if the degree of the numerator is less than the degree of the denominator. All right, so again, a rational function is proper if the degree of the numerator is less than the degree of the denominator. And if a rational function is proper, then the line y is equal to 0 is a horizontal asymptote of its graph. Okay, so if the degree on top is less than the degree on bottom, then your graph is going to have a horizontal asymptote at y is equal to 0. All right, if a rational function r of x, which is equal to p of x divided by q of x, is improper. So that is, if the degree of the numerator is greater than or equal to the degree of the denominator, 3 possibilities may arise. Okay, so again, if your rational function is improper, that means the degree on top is greater than or equal to the degree on bottom. 3 possibilities may arise. So possibility 1 is if the degree of p of x is equal to the degree of q of x. Okay, so if the numerator and denominator are polynomials that have the same degree, then the line y is equal to the leading coefficient of p of x divided by the leading coefficient of q of x is a horizontal asymptote of the graph of R. So again, leading coefficients, those, when you see that term, that just means you are finding the coefficient of the highest degree term. Okay, that's what leading coefficient means. Okay, second possibility is if the degree of p of x, the numerator, is 1 larger than the degree of q of x, the denominator, then the function r of x has an oblique asymptote. And we find the oblique asymptote by long dividing the denominator q of x into the numerator p of x. So if the degree on top is 1 more than the degree on bottom, that means the function has an oblique asymptote, and we can long divide the denominator into the numerator to find that oblique asymptote. Possibility number 3 is if the degree of p of x, so the degree of the numerator, is 2 or more larger than the degree of q of x, then the function r of x has no horizontal asymptote or oblique asymptote. Okay, so again, if the degree of the numerator is 2 or more larger than the degree of the denominator, then the function has no horizontal asymptote or oblique asymptote. Okay, so let's take a look at a few examples, kind of tying everything that we've looked at in this lesson together. Okay, so the directions here say given the function r of x, we are asked to find the domain, the intercepts, so we want to find the x and y intercepts, asymptotes, so does it have a vertical asymptote, a horizontal asymptote, an oblique asymptote, and or holes. So we haven't talked about like when rational functions have holes yet. We'll actually look at that with one or two of the examples that we are going to look at here. Okay, so if we want to look at number 1, the function r of x is 3x divided by x squared minus 9. So first thing we want to see with this function is the rational function in lowest terms? Okay, so to determine that, we want to factor both the numerator and denominator and see if there are any like factors that we can eliminate. So the numerator is already factored, it's 3x. The denominator, x squared minus 9, that's the difference of two squares. That's going to factor to x minus 3 times x plus 3. Okay, so let's just work through this in order here. So if we want to find the domain, we know that our function, our rational function, cannot have values that make our denominator 0. So the two values that make our denominator 0 are 3 and negative 3. So our domain is going to be the set of x such that x can't be equal to negative 3 and x can't be equal to 3. Okay, let's do the x-intercept next. So again, if you guys remember back at the start of this lesson, we said that if our rational function is in lowest terms, the zeros of the numerator tell us the x-intercept. So the value that makes the numerator 0 is x is equal to 0, okay, which is going to be the ordered pair 0, 0. And just as with polynomial functions, when we have rational functions, the degree of the 0 in the numerator tells us, or the multiplicity of the 0 in the numerator, it tells us whether our graph touches or crosses the x-axis at that point. And since that has a multiplicity of 1, it's odd. That means that the graph is going to cross the x-axis at that point. So I'm going to put a C next to that point to indicate that the graph is going to cross. Okay, now the way that we algebraically find the y-intercept of a function is we can plug 0 in the place of x and solve for y. Okay, so when I plug 0 in the place of x, that makes the numerator 0, the denominator negative 9. So that's going to make y equal to 0 divided by negative 9, which is going to be y is equal to 0, which is also going to be the ordered pair 0, 0. Okay, so again, we let x equal 0 and solved for y. Okay, let's do the asymptotes next. Okay, so I'm going to do the vertical asymptotes first. So the vertical asymptotes for this function are going to be the zeros of the denominator in lowest terms. So our rational function is in lowest terms. The values that make our denominator 0 are x is equal to 3 and x is equal to negative 3. Again, we have to write the vertical asymptotes as the equation of a vertical line. Okay, now if we want to find the horizontal asymptote, and this function does have a horizontal asymptote, we are going to compare the degree of the numerator to the degree of the denominator. Okay, so the degree of our numerator is 1. The degree of our denominator is 2, so the degree of the numerator is less than the degree of the denominator, which makes this rational function proper. And if the rational function is proper, then it has a horizontal asymptote at y is equal to 0. Okay, let's take a look at number 2. So for number 2, we have the function x cubed. So the function r of x equal to x cubed over x squared minus 4. Okay, so same thing here. We want to check to see if this rational function is in lowest terms. The numerator is factored completely. The denominator is the difference of two squares. That's going to factor to x minus 2 times x plus 2. Okay, so we're going to work through our steps in order. So step 1, we want to calculate the domain. We know that x cannot be equal to negative 2 and x cannot be equal to 2 because those are the two values that make our denominator 0. Okay, if we want the x-intercepts, that's going to be the zeros of the numerator in lowest term. So the value that makes the numerator 0 is x is equal to 0, which is the ordered pair 0, 0. And the multiplicity of that 0 is 3. It's odd, so the graph is going to cross the x-axis at that point. Okay, y-intercept. If we want to find the y-intercept, again, we're going to plug 0 in the place of x and solve for y. So when we do that, we get y equal to 0 divided by negative 4, which makes y equal 0, which is going to be the ordered pair 0, 0. Okay, vertical asymptotes. So the vertical asymptotes here are the zeros of the denominator in lowest terms. So that's going to be x is equal to 2 and x is equal to negative 2. And then the other asymptote that this graph has is an oblique asymptote. Well, how do I know that? I know the graph has an oblique asymptote because the degree of the numerator is 1 larger than the degree of the denominator. Okay, so if we want to find the equation of the oblique asymptote, I have to long divide the denominator into the numerator. So I need to long divide x squared plus 0x minus 4 into x cubed plus 0x squared plus 0x plus 0. Okay, so we want to think to ourselves, what times x squared gives us x cubed, and that is x. Then we're going to distribute x across all three terms out front, so that's x cubed plus 0x squared minus 4x, and then I'm going to subtract the result, which gives me 0x squared plus 4x, and we bring down the next term in line, which is plus 0. What times x squared gives us 0x squared? That is 0. So when I distribute 0 across everything, we get 0x squared plus 0x plus 0. And then when I subtract, my remainder here is 4x. Okay, now when it comes to finding oblique asymptotes, I can't explain this fully until you guys get into calculus. But when you find a remainder like we found here, you ignore the remainder when finding the oblique asymptote. So our oblique asymptote is going to be this. It's going to be the line y is equal to x. Again, when you guys get into like calculus, so whenever you learn about calculus in pre-calculus next year, I'll be able to explain why that remainder goes to 0. Okay, I just can't do it with what you guys know right now. Okay. Let's take a look at number 3. We'll do 3 together, and then I'll let you guys try number 4 on your own. So for number 3, we have the function r of x equal to x squared minus 25 over x squared plus 2x minus 15. So again, step 1 for us here is to check to see if this rational function is in lowest terms. So I'm going to factor the numerator and denominator. So numerator is the difference of two squares, factors to x plus 5 times x minus 5. And our denominator, that is going to factor to x plus 5 times x minus 3. So when we look at this, we see that the rational function is not in lowest terms. Now, if your rational function is not in lowest terms and you're able to cancel factors like we have here, that tells you that your graph is going to have a hole. So we'll talk about how we find the coordinates of the whole at the very end. Okay, so let's do our domain first. So our domain, the values that make our denominator 0 are -5 and +3. So our domain here is going to be the set of x such that x can't be equal to -5 and x can't be equal to +3. Okay, next we want to do the x-intercepts. So the x-intercept here is going to be the 0 of the numerator in lowest terms. So in lowest terms, my function is x minus 5 over x minus 3. So the value that makes our numerator 0 is when x is equal to 5, which is the ordered pair 5, 0. Again, the multiplicity of that is 1, so the graph is going to cross the x-axis at that point. Okay, if you want to find the y-intercept, you plug 0 in the place of x and solve for y. Now, it doesn't matter if you do it in the original function or if you do it in the simplified function, you're going to get the same result either way. So when we plug 0 in the place of x and solve for y, we get -5 over -3, or -25 over -15, which simplifies to -5 over -3. So that's going to make y equal to 5/3, which is the ordered pair 0, 5/3. Okay, vertical asymptotes. So the vertical asymptotes are going to be the zeros of the denominator in lowest terms. So in lowest terms, the only 0 our denominator has is when x is equal to 3. So that right there is going to be the vertical asymptote for that function. Let's find the horizontal asymptote next. So again, it does not matter if you do the horizontal asymptote with the original function or the simplified function. I'm going to do it with the simplified function. Okay, so when I look at the simplified function, the degree of the numerator is 1. The degree of the denominator is also 1. So if we want to find the horizontal asymptote, it's going to be equal to the line y is equal to the leading coefficient on top, which is 1, divided by the leading coefficient on bottom, which is 1, and 1 divided by 1 is just 1. So that has a horizontal asymptote at y is equal to 1. Okay, so we also said that this graph here has a hole. Let's talk about how to find the coordinates of the hole. Okay, so if you want to find the coordinates of the hole, what you do first is you look at your canceled factor and the value of x that makes that canceled factor 0, that is going to be the x coordinate of your hole. So the value that makes x plus 5 0 is the x value of -5. And then what you're going to do is you're going to take that x value and you're going to plug it into the simplified function to figure out the y coordinate at that x value. So when I plug -5 into the simplified function, we get -5 minus 5, which is -10. Whoops. I'm going to erase this here in 1 second. So that's -10. And then on bottom, we get -5 minus -3, which is -8. And -10 divided by -8, that is going to simplify to +5 over 4. Okay, so that right there is going to give you the coordinates of your hole. Okay, you guys give 16 a try. Excuse me, so for 16, you have r of x equal to x squared minus 16 divided by x squared plus 2x minus 24. Okay, so let's check and see how you did with this. So again, we want to check and see if this is in lowest terms. So the numerator factors to, it's a difference of two squares. It's x minus 4 times x plus 4. And your denominator factors to x plus 6 times x minus 4. So we are able to eliminate that common factor of x minus 4, which is great. So that means that our rational function in lowest terms is x plus 4 over x plus 6. Okay, so let's go ahead and figure out what we're asked to find here. So domain, the two values that make our denominator 0 are x is equal to negative 6 and x is equal to 4, and we know that x can't be equal to either one of those two values. Okay, next, x-intercepts. So those are going to be the zeros of the numerator in lowest terms. So the only value that makes the numerator 0 in lowest terms is x is equal to negative 4, which is the ordered pair negative 4 comma 0. It has a multiplicity of 1, so the graph is going to cross the x-axis at that point. Okay, y-intercept, again, doesn't matter if you plug into the original function or the simplified function. You're going to get the same thing either way whenever you simplify. So I'm going to plug into the simplified function. When I plug 0 in the place of x, we get y equal to 4 over 6, which makes the y-intercept become y is equal to 2/3. So that's the ordered pair 0 comma 2/3. Okay, vertical asymptotes. Those are the zeros of the denominator in lowest terms. So in lowest terms, the only value that makes the denominator 0 is x is equal to negative 6. Again, this has a horizontal asymptote. Doesn't matter if you check with the original function or the simplified function. Again, I'm going to do the simplified function. So with the simplified function, the degree on top is 1. The degree on bottom is 1. Since the two degrees are the same, the line y is equal to the ratio of the leading coefficients is a horizontal asymptote. So the leading coefficient on top is 1, leading coefficient on bottom is 1. 1 divided by 1 is 1. So the line y is equal to 1 is a horizontal asymptote. And just like the previous example, this example also has a hole. So again, the x-coordinate of the hole is the value that makes the canceled factor 0. So the value that makes the canceled factor 0 is 4. And then we're going to plug 4 into the simplified function to figure out what the y-coordinate is. So when I plug 4 in the place of x in that simplified function, we get 4 plus 4, which is 8, over 4 plus 6, which is 10. So that has a y-coordinate of 4/5. Okay? And that'll give you right there everything that you need to be able to know in order to sketch the graphs of rational functions. So you have to have a really good understanding of these properties to be able to graph those rational functions. Okay, so I'll post the videos on graphing rational functions later on this week. Hope you guys have a great day. Take care.